Hey everyone, welcome back to Chem Story. Hope you're all doing great today. We're diving into one of the most fundamental topics in chemistry, acids and bases. Now when it comes to defining acids and bases, there are three major definitions we use: the Arrhenius Definition, the Brønsted-Lowry Definition, and the Lewis Definition. Each one gives us a different way of thinking about how acids and bases behave. And by understanding how these definitions compare, we can do a much better job analyzing all kinds of chemical reactions. Let's start with the Arrhenius definition. This is the most traditional way of defining acids and bases. According to this idea, acids are substances that release protons when dissolved in water. These protons don't stay alone for long. They quickly associate with water molecules to form hydronium ions. On the other hand, bases are defined as substances that increase the concentration of hydroxide ions in aqueous solution. For example, when hydrochloric acid, HCl, dissolves in water, it dissociates into H3O+ and Cl-, and that's what makes the solution acidic. Likewise, when sodium hydroxide, NaOH, dissolves, it breaks apart into Na+ and OH-. That increase in hydroxide ions makes the solution basic. But here's the problem. This definition only works in aqueous solutions. In other words, it doesn't help us understand what's going on in organic solvents, or how acids and bases behave when they're not dissolved in water. It also doesn't explain reactions that don't involve hydroxide ions at all. That's why we need a broader definition, one that works beyond just water-based reactions. And that brings us to the Brønsted-Lowry theory. The Brønsted-Lowry definition takes acid-base chemistry a step further because it focuses on proton transfer, not just what happens in water. According to this definition, a Brønsted-Lowry acid is a proton donor. It gives up an H+ ion. A Brønsted-Lowry base, on the other hand, is a proton acceptor. It takes in an H+ ion. This definition is way more flexible than the Arrhenius definition because it works not just in water, but in all kinds of other solvents too. Now, let's look at an example. When HCl reacts with water, the HCl molecule donates a proton to H2O, forming H3O+ and Cl-. So in this reaction, HCl is the Brønsted-Lowry acid because it donates a proton. Water, on the other hand, acts as the Brønsted-Lowry base because it accepts that proton. And once the proton is transferred, HCl becomes Cl-, which is its conjugate base. Water becomes H3O+, which is its conjugate acid. This idea of conjugate acid-base pairs is super important because it helps us understand how acids and bases behave in equilibrium reactions. So why is the Brønsted-Lowry definition so useful? Well, it works in non-aqueous solutions too, which makes it way more versatile than Arrhenius. But wait, what about reactions where there's no proton transfer at all? Can we still call those acid-base reactions? That's where we need an even broader definition, the Lewis definition. The Lewis definition is a whole different approach because it doesn't focus on protons at all. Instead, it's all about electron pairs. A Lewis acid is anything that accepts an electron pair, while a Lewis base is something that donates an electron pair. This is the most general definition of acids and bases because it still works even when there are no protons involved at all. A great example of a Lewis acid-base reaction is BF3 reacting with diethyl ether. In this reaction, BF3 acts as a Lewis acid because the boron atom is electron deficient and has an empty p orbital that can accept an electron pair. Diethyl ether, on the other hand, acts as a Lewis base because the oxygen atom has a lone pair it can donate to BF3. And here's the key point. There's no proton transfer happening at all. That means neither the Arrhenius definition nor the Brønsted-Lowry definition can explain this reaction. But the Lewis definition can. The best part about the Lewis definition is that it explains a much broader range of acid-base reactions, especially in organic chemistry. A lot of important reactions, like electrophilic and nucleophilic interactions, make the most sense when you look at them through the lens of Lewis acids and bases. It's also incredibly useful in transition metal chemistry, where metal ions often act as Lewis acids, accepting electron pairs from ligands. Because it applies so broadly, the Lewis definition is considered the most comprehensive acid-base theory we have. It helps us explain reactions that the other definitions just can't. That's why, in so many cases, chemists rely on the Lewis acid-base concept to analyze complex reactions, whether it's in organic, inorganic, or coordination chemistry. Now, let's make a connection between Brønsted-Lowry acids and Lewis acids. When a Brønsted-Lowry acid donates a proton, or H+, it also accepts an electron pair from the base. And if you think about it, that fits perfectly with the Lewis definition, because a Lewis acid is anything that accepts an electron pair. So here's something interesting. Every Brønsted-Lowry acid is also a Lewis acid. Why is that? Because when an acid donates a proton, it's actually accepting an electron pair at the same time. In other words, proton donation and electron pair acceptance go hand in hand. But here's something important to keep in mind. Not all Lewis acids are Brønsted-Lowry acids. Take boron trifluoride, BF3, for example. It's a Lewis acid because it accepts an electron pair, but it doesn't donate any protons. And since the Brønsted-Lowry definition is all about proton transfer, BF3 doesn't count as a Brønsted-Lowry acid. So here's the key takeaway. The Lewis acid definition is broader. It covers not just proton transfer reactions, but any reaction where an electron pair is accepted. And that's exactly why it's so useful in organic chemistry, and in coordination chemistry too. To summarize, each acid-base definition has its own strengths. The Arrhenius definition is great for aqueous solutions, but it does have its limitations. The Brønsted-Lowry definition builds on that by focusing on proton transfer, which makes it more flexible. And the Lewis definition is the most comprehensive because it explains reactions in terms of electron pair interactions, which makes it super useful in both organic and inorganic chemistry. So which one's the best? Well, it really depends on the type of reaction you're looking at. If it's happening in water, Arrhenius works just fine. If it involves proton transfer, Brønsted-Lowry is the way to go. And if you're dealing with electron movement, especially in organic or coordination chemistry, Lewis is your go-to. The key is being able to look at acids and bases from different angles. That's what really helps you understand the bigger picture in chemistry. All right, that wraps it up for today. Keep these definitions in mind because they're going to be super helpful as we dive deeper into acid-base chemistry. See you next time.